Hello and welcome. This is the course on stochastic modeling and the theory of queues. In this lecture, we will look at network of queues. We will start off by looking at a tandem or a sequence of MM1 queues. We will see how Burke's theorem and the Poisson thinning process property can be used to make the analysis of tandem of MM1 queues simpler. Then we will generalize and look at a network of queues. We will distinguish between open and closed network of queues, and then we will see how the Jackson's theorem can be successfully applied to analyze network of queues. So let's first consider a tandem or a sequence of two MM1 queues. We have Q1 here, which takes an external arrival of customers, and the customers who leave Q1 directly go into the second queue, Q2. Let lambda be the arrival rate of the customers to the first queue. At this point, we do not know the arrival rate behavior to the second queue. Let mu1 be the exponential service rate of the server present in the Q1. Let mu2 be the exponential service rate of the server present in Q2. This is a tandem of queue. There are two, the waiting space in Q1 as well as Q2 have no constraints, so it is basically an infinite buffer queues. We know that by applying the Burke's theorem, which tells that in an MM1 queue, the departure process is also Poisson and it has the same rate as that of the arrival process. So the departure process of the Q1 is also a Poisson process with rate lambda, which is the same rate at which customers arrive to Q1. And the arrival of customers to Q1 and of course the service is not dependent upon the behavior of Q2. Therefore, by Q1 itself is an independent MM1 queue. And because we know that the arrival process for Q2 is Poisson, and naturally the service process is independent of the arrival to Q2. Q2 is also an MM1 queue and its behavior is independent of the first queue, excepting for the rate. The arrival rate to the Q2 is fixed by the arrival rate of Q1. Given that as lambda, then Q2's behavior is independent of Q1 in the statistically. So what this allows us is that let N1 be the number of customers who have arrived at the time to Q2, and N1 to Q1 and N2 to Q2. Then because these two are independent MM1 queues, the number of customers at any given times in Q1, if you call it as N1, and the probability that N1 is equal to I is simply given by the MM1 formula for the number of customers in the queuing system, which is 1 minus rho 1 into rho 1 power I, where rho 1 is the server utilization factor of Q1, which in turn is lambda by mu1. Similarly, for the case of Q2, we get the probability that N2, the number of customers in the second queuing system, to be J, is again given by the standard formula, which is 1 minus rho 2 into rho 2 power J, where rho 2 is the server utilization factor for the second queue, which is again lambda by mu 2, where lambda is the same as the external arrival rate to the Q1, which follows from the Burke's theorem. Therefore, because these two are independent Qs, we can even write probability that N1 is equal to I and N2 is equal to J is the product of probability N1 is equal to I into the probability that N2 is equal to J, which again boils down to 1 minus rho 1 into rho 1 power I into 1 minus rho 2 into rho 2 power J. We can also see this by doing a detailed analysis, which we will do it now. So, we have one MM1Q feeding to another MM1Q. Now, we will take the following quantities as given. The lambda 1 is the lambda 1 is the arrival rate to the first Q1, mu 1 is the service rate for the first Q1, mu 2 is the service rate for the second Q2, that is the second Q. Okay. And Burke's theorem is basically follows from the time reversibility property, and because of that it tells that the departure process of the MM1Q is also Poisson with the same rate as that of the arrival process, and the number of customers at any given time in the queue is independent of the sequence of departures that has taken prior to that time. So, these two are the important properties that we will make use of. Now, what we will do is we will try to analyze this system. We will consider the state of this system to be a combination of the number of customers in the first queuing system followed by the number of customers in the second queuing system. So, we will use a pair n comma m, where n is the number of customers in the first queuing system and m is the number of customers in the second queuing system. Taking this as the state space, we can come up with a Markov chain, and we can look at the detailed balance condition of the Markov chain. We have not drawn the Markov chain, but it is easy that we can write down the detailed balance condition. So, when Nm is equal to 0, 0, it means there are no customers in the first queuing system as well as second queuing system, and so on. So, we will just look at the following thing, P00. So, if you look at the, look at the detailed balance condition between P0, the 00 state and the 01 state. Okay. So, the balance equation reads as follows, because the only way we can leave the state P00 to 01 is by an arrival of a customer. Okay. And the way we can come back to 00 from 01 is when a customer departs from the second queue. Of course, there are no customer in the first queue, so only a customer in the second queue can depart. That is the only other event that is possible. So, these two events, the corresponding probability, if we equate it, lambda into P00 is an arrival of a customer to 00 states, which will lead to 01, and mu2 into P01 is the probability of departure of a customer in the second queue, which will also make the second queue empty, P00. Okay. Then we will look at the next equation. Let us look at Pn0, which means there are n customers in the first queuing system and 0 customers in the second queuing system. Under this condition, what are the departures from N0? What transitions take you out of N0? when a customer arrives or when there is a service completion in the first queue, we will depart from n0. So lambda into Pn0 is one thing, mu1 into Pn0 is one thing. So lambda plus mu1 into Pn0 or the transition, the probability with which we will leave n0. How do we come to n0? You can come from n minus 1 comma 0 on an arrival. When a customer arrives, the customer will arrive to the first queue, therefore n minus 1 will become n, while the second queue is not affected. Or if there are n customers in the first queue and one customer in the second queue, and if that customer departs at a rate mu2, we will again go to n0. So mu2 into Pn1 will also lead you to n0. So this is the other equation. Then we will look at the other case when there are 0 customers in the first queue and m customers in the second queue, and look at the detailed balance. What will take you out of 0m, or as a result of an arrival of a customer or a departure of customers in the second queue? See, look at, because the first queue is empty, there is no concept of service completion in the first queue, so mu1 will have no role here. So lambda plus mu2 into P0m is equal to mu1 into P1m minus 1. So what will happen? If the customer in the first queuing system the service gets completed, the Q1 becomes empty, it will become 0, and here there will be an increase in the number of customers in the second queuing system. So from 1 m minus 1 we will go to 0 m. On the other hand, if there are 0 customers in the first queue and m plus 1 customer in the second queue, on a departure from the second queue, this m plus 1 will become m. So this is the second balance condition. In general, if we have n comma m customers in the first and second queuing system respectively, the events that will take you out of it are either an arrival of a new customer or a service completion in either the first queue or the second queue. Therefore, lambda plus mu1 plus mu2 into Pnm is equal to, so to get into n comma m, if you have an arrival when there are n minus 1 customer in the first queue, the arrival will increase n minus 1 to n, that is a possibility. Or when there is n comma m plus 1, service completion in the second queue will decrease m plus 1 to m. Or if you have n plus 1 customer in the first queue with m in the second queue, a service completion, okay, sorry, this has to be m minus 1, correct, because a service completion in the first queue will take a customer from the first queue and send it to the second queue. So n plus 1 will become n, and whatever it is in the second queue will increase by 1. To come to m, it has to be m minus 1. So this is a correction that you have to do. So we have written the detailed balance condition, you can solve it, okay, and if you solve, you will get the general state occupancy probability of this bidimensional Markov chain. Pnm can be obtained. We can see that this will be the product of the probability that there are n customers in the queuing system into m in the second queue, which we already obtained through Burke's theorem. In which case you will have rho 1 power n into 1 minus rho 1 into rho 2 power n into 1 minus rho 2. Rho 1 is lambda by mu 1, rho 2 is lambda by mu 2. This is what you would get. The other way to check is that if assuming that the solution Pnm is given of this form, To check whether it is right, if you substitute this P and M in all these 4 equations, if it gets solved, then it shows that this is indeed a valid solution, because these are the only 4 equations that needs to be solved. Suppose we start off with a probability of this form, and if it gets solved, it will be a limiting probability and hence stationary. To just check, we can just check whether for the first equation whether it gets solved. In the case of the first equation, you will see that lambda into P00, okay, if whether it is equal to mu2 into P01. So you will see that P00 is lambda by mu1 power 0 into 1 minus lambda by mu1 into lambda by mu2 power 0 into 1 minus lambda by mu2 into a lambda will be there. That is equal to P01 mu2 times mu2 should be there into this is lambda by mu1 power 0 into 1 minus lambda by mu1 into lambda by mu2 power 1, because it is P01 into this one. So actually there should be a lambda here, there should be a mu2 here, there has to be an mu2. So you would see that this is 1, this is also 1, we have only this much remaining. So you would see there will be a lambda here, because lambda by mu2 into mu2 gets cancelled, you will have a lambda. That is a very simple way of checking whether this is true or both are true. So it indeed solves the first equation. In a similar manner, you can check whether other equations are solved. Well, now what is that we have obtained? We have shown that in a case of tandem of MM1 Qs, because of the Burke's theorem and the basically we can say that they are all, we can treat them as independent Qs, and the probability of the state occupancy, the number of customers in a queuing system, is given by the product of the probabilities. That is the most important inference from this our discussion. Then we can apply it to find the total number of customers n in the combined queuing system. To check to find the probability that there are capital N customers, or if you want to find the average number of customers in the overall queuing system, cap N if you want, then what you have to do is you have to sum it over all possible events of n plus m, which all leads to n plus m equal to capital N plus m, such that n plus m, okay, all possible pairs of n plus m, for each n plus m we have to multiply it by P of n comma m, which is given by this equation. Okay. So we will see that. So we can write n plus m into P1, P n comma m can be written as Pn into Pm, which is again this n plus m, we can make it as product of two summations. We can write this as sigma over n, npn to sigma over m pm, mpm to be right. Okay. So sorry, yeah, this way, sigma over n npn plus sigma m pm plus sigma n pn into sigma m mpn. That way we can write. You would see that this is 1, similarly this is 1. So what we get is sigma n npn plus sigma m mpn, which is nothing but the average number of customers in the first queuing system plus the average number of customers in the second queuing system. So if you have a tandem of two queues, the average number of customers in the entire queuing system is the sum of the average number of customers in each queue in the sequence. You can extend it even if you have a tandem of n queues, many queues, 10 queues. The average number of customers in the entire queuing system is the sum of the averages. Okay. So this is for a sequence of queues. We will now look at a network of queues where there can be feedback in the queues. That is, customers do not leave one queue and go to the next queue in a particular order. Okay. So there can be external arrivals to any arbitrary queues, and a customer on completing a given queue may go to a queue which is not necessarily next in that order, and so on. So general network of queues is what we are going to look at. The examples can be customers from one queue can join a queue in the bank, okay, or a post office, supermarket, and so on. For example, if you want to go and open a new account, you first go to a first teller. The teller may ask you to go to another place where you have to give your credentials, you have to give your address proof and then identification proof and all those things. After coming it again, you have to come, they will issue a new passbook, then they will ask you to go to another queue where you have to make an initial deposit. After making an initial deposit and taking a challan, you have to go and then again update your passbook, and so on. So you may have to return to the same queue for some reason, or in some case, if there is a clarification that is required in one teller, you may have to go to some other place, get it clarified, and then come back. Similarly, in a computing system, a given job, okay, first go to the CPU, it runs for some time. Because of some IO requirement, it is being put in a state, okay, called as a sleep mode. After completing the IO operation, it will come back and run for some time, and so on. So in a typical environment, okay, multi user environment, many processes will be running and it will be scheduled following a scheduling algorithm. They will go between CPU, IO, memory, or even some network operation, and so on. The same is true for also a packet in computer networks. So we can classify the queuing system into open queuing system, closed queuing system, and mixed queuing system. In the case of the open queuing system, you have customers arriving to one of the queue in the ensemble of queues, network of queues. They will visit certain queues and then eventually depart. Okay. So every arriving customer go through some sequence of queue, may revisit some queues in that process, but eventually depart. In the case of closed queuing system, there are no arrivals, no departures. There will be set of entities which will move between queues in some order, not necessarily in sequence as shown here, some order, and they will remain there forever. For example, if you look at a computing system where there may be many background processes that will be there, some process which will, like a printer daemon process, which will just look if there is a job for printing, if so it will do the job and then go to the background. Similarly, some job which does the memory management, a job which does the scheduling, some which does the garbage collection, and so on. So these are all background processes which should always be running in the sense not actively in the CPU, but it will be in the alive state. Okay. So once they are being forked, and they will remain in this stage until the system is shut down. They will be either in this blocked mode or it will be the running mode. So there are no arrivals, no departures. This is a kind of a closed system. There can also be a mixed systems where some of the processes are background which will only remain in the system and move between the system forever, while there are some external arrivals, some departures, and so on. So here we will make use of this kind of queues. We will call it as a Jackson's queue because its a powerful theorem has been proved by Jackson's, and such queues are modeled as a collection of MMN queues which can have feed forward or feedback within this system. So we have got an open queuing system in general. Okay, if that is more general because okay, or a mixed queuing system is more general, which can either be open or it can be closed. We will assume that each queue is assumed to be an MMN queue with the following the FIFO service discipline. The service time of each queue is assumed to be exponentially distributed with a parameter mu, independent of the service that happens in the other queues. Then there can be external input sources to every queue with a Poisson arrival rate with a parameter lambda. Upon departure from a particular queue I, the customer can be routed to another queue, say J, with a routing probability Pij. So from each queue there is a finite probability with which a customer go to some other queue J, which may also include I, or they can depart from the queuing system. So that the probability of exit is 1 minus sigma j Pij. Again the sigma is missing here. 1 minus sigma j Pij. Sigma Pij is the probability of going from after departure from ith queue to jth queue, including I. Sigma is the probability of, you can call it as recirculating in the queuing system. With 1 minus sigma j Pij, you depart the entire queuing system. And this is the external arrival rate. We will consider this kind of an queuing system. To start off with, we will look at a very simple system and then see how the Burke's theorem and the Poisson thinning process makes the analysis simple. You have three queues, Q1, Q2, Q3. Lambda is the external arrival rate to Q1, and you would see that by the Burke's theorem, the departure process from the Q1 is also a Poisson process with the same rate lambda. So we can take this as lambda. Let us assume that with the probability P, a customer on leaving Q1 goes to Q2. So the P12, what we saw in the generic case here, is P, and with 1 minus P, the customer from Q1 goes to Q3. So a customer from Q1 don't exit, they either go to Q2 or Q3, while customers on completing service on Q2 and Q3 always leave. So like this. So applying the Poisson thinning process, we can see that because this P is with a probability P, a customer joins Q2, okay, independent of the service that happens. So because of that, this process which governs the entry or arrival to Q2 is also a Poisson process with a parameter lambda times P. This follows from the Poisson thinning process theorem. Similarly, the arrival process to Q3 is also a Poisson process with parameter lambda into 1 minus P. Again, applying the Burke's theorem, the departure process of Q2 is Poisson with the same parameter as that of the arrival to Q2, which is lambda P. Similarly, for Q3, the departure process is Poisson with a parameter lambda into 1 minus P. So we have arrived at the arrival rates to each of this Q1, Q2, Q3. If you know the service rates of each of them, we can treat them as independent queues, and we can write down the probability that there are N1 customers in Q1, N2 in Q2, N3 in Q3. How is rho 1, rho 2, rho 3 can be calculated using this lambda lambda p, lambda into 1 minus p are the respective arrival rates, mu1, mu2, mu3 are the respective service rates. Using that, you can find rho 1 power n1 into 1 minus rho 1, rho 2 power n2 into 1 minus rho 2, rho 3 power n3 into 1 minus rho 3, and so on. Next, we will consider another process where there is which is a feed forward network of queues. But there are two arrivals that take place. So you have a queue Q1 to which arrival occurs at the rate Poisson arrivals occur at a rate lambda 1, and to the Q2 there is an external arrival as well as customers departing from Q1 can occur. So lambda 2 is the external arrival to Q2. The probability P with respect with which a customer from Q1 goes to Q2 is 0.4. Similarly, with the probability 0.4, a customer from Q1 goes to Q3, 0.2, the customer from Q1 goes to Q4. All customers departing from Q2 as well as Q2 goes to joins to Q4, whereas from Q3 with a probability 0.6 they go to Q4, 0.4 they leave. All customers from Q4 leave. So this is the queuing system. So from this one what we can do is we can write out by applying Burke's theorem and Poisson thinning process, we can find the effective or overall arrival rate to each and every one of these queues. Once we know the service rate of each of these queues, you can treat them as independent M1 queues, and all probability of occupancy of the customers in these queues, joint probability of occupancies can be found out. For finding the effective arrival rate, we use the condition of that we have just seen. For example, in this case, you can I will just tell you. Yeah, you can just look at this one. So you can first find lambda 1 will be the departure, Poisson rate of the departure process of Q1 from Burke's theorem. So if you look at lambda, if you consider lambda 2 as we will take lambda 1, lambda 2, lambda 3 and lambda 4 are the respective arrival rates of Q1, Q2, Q3, Q4. Lambda 1 is given, which is external. Sorry, this is lambda 2 by, okay. We will call the arrival rate to Q2 is lambda 2 plus 0.4 times lambda 1. The arrival rate to Q3 is 0.4 lambda 1. And the arrival rate to Q4 is 0.2 lambda 1 plus lambda 2 plus 0.6 lambda 3. Okay. So this way we can find the effective arrival rates to each of this queue, and that will, okay, all these can be arrived at, and then you can find the probability that there are certain number of customers in Q1, Q2, Q3 and so on. So in general, for a system of a network of k queues, the arrival process of a given queue Qi has two parts: external arrivals to the queue, call it as capital Qi, plus sigma j varies from 1 to k, where there are k queues of jobs that finish from their jobs from jth queue and then routed to the Qi. Using this general formula, external arrival plus sigma j varying from 1 to k of lambda j into p ji will give you the arrival, overall arrival to ith queue. So lambda I can be given as delta I, which is the external arrival to ith queue, plus sigma. So I think this would be better. If it is lambda I, you have to put it as j. sigma j is equal to 1 to k lambda j pij, lambda j pj, or if you want the right equation is if you put lambda j is equal to delta j plus sigma I varies from 1 to k lambda I pij. So that way we can solve it. So what Jackson's theorem tells you is, consider m queues in a network of queuing system. The state of the system, if it is represented as an m tupule where each component is the number of customers in each one of these queues. So n is as a combination of n1, n2 to nm, which are the respective number of customers into queues 1 to m. Ni represents the number of customers in the ith queue. So this network of m queues we can be treated to be a combination of m independent queues, and therefore the probability that n1 is equal to small n1, n2 is equal to small n2 and so on can be written as a product of p of n1 is equal to n1 into probability that n2 is equal to n2 and so on. That is pi I varying from 1 to m pi of ni, where in turn pi of ni is given by 1 minus rho I power ni, where again rho I is given by lambda I by mu I. So this is the powerful theorem that can be used to consider a network of m moment queues. That is what we call as the Jackson's theorem. We will try to apply it for this queuing system where there is a feedback now. Again, this is one of the simplest possible system where there is just two queues with one feedback. Lambda is an external arrival rate and there is a feedback here. So there is a these two customers from the external arrival rate and what is being fed at a rate lambda 2 are statistically multiplexed and given to this queue, which is used to model the CPU of a computer. This queue models the I/O system of a computer. The service rate of CPU is mu1, service rate of I/O is mu2. Both are exponential service rate. So how do we analyze it? We will call this arrival rate as lambda 1. We can see that lambda 1 is nothing but lambda plus lambda 2. And because lambda 1 is the arrival rate to first queue, the departure process of the first queue, CPU queue, is again Poisson with the same rate lambda 1. Let us assume that jobs which complete the CPU cycle with a probability P1 it leaves the system, with a probability P2 which obviously is to be equal to 1 minus P1, it goes to I/O. On completing I/O again it goes to enters the CPU. So P1 lambda 1 is the rate at which jobs from completing CPU completes and leaves the system. P2 lambda 1 is equal to lambda 2, which is the arrival rate to the second queue, I/O queue. Again using the Burke's theorem, the departure of the I/O queue is also lambda 2, which is again Poisson. Again we are, due to statistical multiplexing, we can tell that this combined process is again Poisson process whose rate is the sum of these two things. This is the opposite of the thinning theorem. You can due to statistical multiplexing property of the Poisson process. So we can now write the following thing. First we can write lambda 1 is equal to lambda plus lambda 2. Lambda 1 is equal to lambda plus lambda 2. Lambda 1 is equal to lambda plus lambda 2. That and lambda 2 is equal to P2 lambda 1. These are the two things we will take. So lambda 1 is equal to lambda plus lambda 2 and lambda 2 is equal to P2 into lambda 1. If you substitute this P2 lambda 1 in this place, then we will get lambda 1 is equal to lambda plus P2 lambda 1 on taking it in this side. 1 minus P2 into lambda 1 is equal to lambda. 1 minus P2 is P1. So P1 lambda 1 is equal to lambda. Therefore, we get lambda 1 is equal to lambda by P1. And again, if you substitute this lambda 1 in this place, you will get lambda 2 is equal to P2 into lambda by P1. So now we have got lambda 1 as well as lambda 2. We know mu1, mu2 being the service rate. So we will get rho 1, rho 2. Then probability of n1, n2, n1 under the CPU and n2 in the IO is rho 1 power n1 into 1 minus rho 1, rho 2 power n2 into 1 minus rho 2, where rho 1 is lambda 1 by mu 1, rho 2 is lambda 2 by mu 2. And then we can even find the average number of customers or the jobs in with CPU. We will get, it is nothing but rho by 1 minus rho. Because it is CPU, the average number of job is rho 1 by 1 minus rho 1. Similarly, the average number of jobs undergoing IO operations is rho 2 by 1 minus rho 2. And the total average number of jobs in the system is n bar is equal to n1 bar plus n2 bar, is n1 bar plus n2 bar, which is rho 1 by 1 minus rho 1 plus rho 2 by 1 minus rho 2. Like that you can do. Or we can even consider this as the tandem of queues, okay, need not without worrying about the feedback. And then, but the effective arrival rates have to be changed. Okay, if you S1 is the effective arrival rate, we can see that this S1 is given by lambda by rho 1 is given by lambda 1 by mu 1, okay, but you know that that is equal to lambda by P1, lambda 1 is equal to lambda by P1. So you can see that I am just writing it as in place of S1 into lambda, if you put it, it is lambda by mu1 P1. Similarly here, lambda into S2 is lambda, this is wrong actually, if you in place you have to find using this one. So S2 is nothing but lambda 2 in the lambda into P2 by P1, that is, that you can consider an effective arrival rate to each of this system and consider them to be a tandem of two queues. That is an equivalent representation. We will now apply the Jackson's theorem for the queue shown here as a last example. Again, we will assume for simplicity the service rates are all common for all these four queues. Mu1, mu2, mu3, mu4 are all same, which is 0.5. We have to find the average number of customers in the queuing system. Lambda is the external arrival rate. To the Q1, this is the kind of statistical multiplexing that occurs, and so on. Now, and these are the probabilities with which a customer leaving a given queue goes to the next queue, and so on. So we can write the overall arrival rate. So if you look at this one, Q1, whose arrival rate we will call it as lambda 1, that is given by external arrival rate lambda plus 0.2 times lambda 2 plus 0.2 times lambda 3. So 0.2 lambda 2 plus 0.2 lambda 3 plus lambda is equal to lambda 1. That is one equation. If you look at lambda 2 arrival rate to Q2, it is nothing but 0.4 times lambda 1. Similarly, lambda 3, the arrival rate to Q3 is 0.4 times lambda 1. So lambda 2 equal to lambda 3 is equal to 0.4 lambda 1. Coming to lambda 4, the arrival rate to Q4, it is nothing but 0.2 lambda 1 plus 0.6 lambda 2 plus 0.6 lambda 3. So once we have this, okay, we will be able to solve these equations, and you can get all arrival rates to each one of queues in terms of the external arrival rate lambda. You can get this kind of a solution. Then the server utilization factor can also be found out by dividing it by the mu, which is 0.5 common for all. So you will get rho 1, rho 2, rho 3, rho 4 as given by this one. Then probability that there are n1, n2, n3, n4 customers is simply given by 1 minus rho 1 into 1 minus rho 2 into 1 minus rho 3 and so on. You will see that rho 1 and rho 2, if you look at 2 and 3, will have the same arrival rate. So we can simply say 1 minus rho 2 is equal to 1 minus rho 3, 1 minus rho 2 whole squared we can put it. So 1 minus rho 1 into 1 minus rho 2 whole squared into 1 minus rho 4 into rho 1 power n1, rho 2 power n2 plus n3, rho 4 power n4. Okay. So if you want the average number of customers in the entire queuing system, you have to sum up the average in each and every one of this queuing system. Each, that is n1 bar plus n2 bar plus n3 bar plus n4 bar, and that is given by, each one is given by rho by 1 minus rho of the respective queue. So this is how we can analyze a network of queues using the Jackson's theorem. So we will stop at this point. Thank you.